Hey, hello, everybody. Hey, we're going to talk about Newton's second law in this lecture. And as you probably know, Sir Isaac Newton led to a lot of the way we think of physics today. And technically, it's classical physics, which departs from modern physics, which is what you have with Einstein and the theory of relativity. But we're going to concentrate on Newton's second law. And we have talked about this before, okay? But it can simply be put as force is equal to mass times acceleration. And we've already talked about that. But we're going to add a few things here, okay? So what we're going to do is we're going to say the sum of all the forces. So that Greek letter right there is sigma, and that means sum. And if you guys may remember from elementary school or middle school, sum means to add, just as difference means to subtract, okay? So we're going to take all of the forces, and that is going to equal to our mass times acceleration. So we've already talked about force diagrams, and we're going to kind of continue with this, and we're going to name some of those forces. So if we have, let's say, the ground here, okay, and we have a box, and let's say this is 1 kilogram. Now, what I would like to do in this lecture here is to talk about all the forces. What are all the forces that are acting on this, okay? And one way you can think of this is to say everything that touches it okay, so everything that touches an object plus gravity plus friction plus other. So now that other could be some other force like magnetism or electrostatic repulsion, something like that, okay? But we are not, you guys, we are not going to concentrate on that. Now, you guys are all familiar with friction, even though we haven't talked about it, which we'll talk about it a little bit here. And when we talk about gravity here, we're really talking about weight. And weight is calculated by saying mass times gravity, okay? So just as we have in the previous exercises, we've talked about forces, and we're going to remember forces are a vector, okay? So we're going to say everything that touches it. Now, you guys, what we have here is the ground, okay, right here, 1 kilogram. Okay, the ground here is touching this object. The ground is touching that object. So right here where it touches the ground, we have a vector, and this is known as the normal force, okay? And normal is not what you normally think of it. Normal means perpendicular. Okay, so what we have here is that force is at a right angle to the surface, okay? And the other force, we're going to have plus gravity, okay? Now gravity Now, we could just put mg, okay? Or we could just put f of g. And in the same way, we can say force normal, okay? So we have force normal, force of gravity, okay? Now, you guys, we may have some sort of applied force, okay? So we might have a force that is applied, We're going to push it, okay? Now, we could also have a force that is pulled on it too. But what we want to do is we want to draw an arrow. We want to draw an arrow from the middle of the object or from the edge of the object, and we're going to draw an arrow in the direction that it is going. So even though this force might be coming from the right, we're going to draw this arrow right there, and we're going to have, we can say that that force is applied, okay? And finally, for our purposes, okay, if this ground or this surface, if this surface is rough, as you might expect, there's going to be a force of friction, okay? So that force of friction is going to go in the opposite direction or potential direction of the potential motion. Okay, so we can say here that friction is an opposing force to the motion or potential motion of an object. Okay, so that that is friction. Okay, so what we can see here, all right, is what we have is a free body diagram. Okay, and so what we're going to do is we're going to kind of reduce this picture right there just to dots and arrows that are emanating from those dots. Okay, and so this little dot is going to be the mass. Okay, now technically that is going to be the center of mass. Okay, but we won't worry about center of mass yet. Okay, so now we want to draw this arrow, the normal force. Okay, so we're going to have force normal. We're going to have the force of gravity. We're going to have the applied force, and we're going to have the force of friction. Okay, so in this case, we are going to have two directions, okay? But we can see all of those forces and which direction they're going, okay? So is there going to be any motion? Well, we need some more information, but this is the way we would tell. See, we would say the sum of the forces in the x direction, okay, or horizontal, okay? And that would equal the mass times acceleration, okay, in the x direction. And then we would also have the sum of the forces in the y direction, and that would equal to ma. That would equal to ma. All right? So now let's say right here, as we said, this was 1 kilogram. And let's say this applied force was 10 newtons. And let's say for now that this force of friction was 9 newtons. And we're going to figure out which direction it's going to go. So let's start here with the sum of the forces in the y direction, okay? And that is going to equal to ma. But think about this. If we had a box that was sitting on the ground, would it be moving? Would it be moving? Would it be moving up and down, that is, in the y direction? And the answer is no, okay? Because gravity's pulling it down and the ground is holding it up, okay? So we are going to say that this is 0 just from our situation, okay? So now we can say the normal force that's going up, we're going to call that positive, minus the force of gravity, which is going to be down, and that's equal to 0. That's equal to 0. So now algebraically, we can move this negative force times gravity to the other side. So we can have force normal is equal to the force of gravity, okay? Now, it is not going to, it's not going to matter right now, but later when we talk about the force of friction is dependent on the normal force, okay? But right now we're just saying that it's equal to 9 newtons. So to follow up here, the normal force is equal to the force of gravity, and as I said before, the force of gravity is equal to the weight, and that is equal to mg. So if we say that this is mg, then we can say that force of gravity is equal to 1, and that would be 1 kilogram, times gravity, which is 10 meters per second squared, and that would equal to 10 newtons. Okay, going back to F equals ma. Okay, remember the units. The units to that are newtons, and so we know that is the force of gravity, and we also know that it's equal to the normal force. Okay, so now, you guys, let's talk about the sum of the forces in the x direction. Sum of the forces in the x direction is equal to ma. And now we can look at here. So we're going to say to the right is positive. So we're going to say 10 newtons, which is the applied force, minus 9 newtons, which is the force of friction. And that's going to equal to the mass, which is 1, times the acceleration, which we don't know. So now we can say 10 minus 9 is 1 newton, is equal to 1 kilogram, times A. We divide both sides by 1 kilogram. And you will probably remember that a newton is a kilogram meter per second squared. So in this case, our kilograms will cancel out, and our answer to acceleration will be 1 meter per second squared. So our acceleration is equal to 1 meter per second squared. So that is would be kind of a typical sort of question. So now let's just think about something here for a second. If our force of friction was 11 newtons, okay, if it was 11 newtons, we would kind of go back here and put 11 newtons. And when we did the math, that would equal to -1 meter per second. But that would not be the case because Friction only opposes the motion or potential motion. So in this case, since your frictional force is greater than your applied force, there would be no motion at all. There would not be any acceleration. So even though when you put an 11 there, you would get an answer of -1, the answer is not -1, it would be 0, because the applied force would have to be greater than the acceleration for it to move. Okay, so just a quick review. When we talk about different types of forces, okay, we have a normal force, and that is a perpendicular force that is always going at a right angle to the surface. So if you had a sloped surface, then the normal force would be perpendicular to that, not straight up and down. Okay, the force of gravity is always going straight down, always going straight down. Okay, and we have an applied force. Now, I have this applied force horizontal, but it could be slightly up or it could be slightly down. We're going to probably simplify it and just talk about in terms of the direction that the ground is on. And then the frictional force would be always in the opposite direction of the motion or potential motion. Okay. Now notice here that would have to be parallel. That would have to be parallel to the surface, because this object would not be sinking into the ground and it would not be going up. Okay. Now collectively, when we have this picture, we tend to simplify it just with a dot and arrows, and that will give us what is called a free body diagram. And in a free body diagram, we want everything that touches it, plus gravity, plus friction, plus other. And for our purposes, we won't have another. All right. So until next time, we will talk to you soon.